Welcome back. We now have our Vision in the Loop academic use case concerning real-time monitoring and control in additive manufacturing. I have Brian Booth here from IPE, but we'll first watch the movie.
Hello, I'm Brian Booth, and let's talk about real-time monitoring in additive manufacturing. Now, when I talk about additive manufacturing, what I'm really referring to is the 3D printing of metal parts. And you can see an example of this on the left here, where we've laid down a layer of metal powder, and then a laser goes through it and melts the powder in the pattern of the object that we're trying to build. This process is repeated layer by layer until the full 3D object is printed. Now, the challenges here are, first of all, we have to be very precise, especially with the temperature of the metal. If the metal gets too cold, then the powder doesn't melt properly. But if the metal gets too hot, then you risk damaging the layers that you've already printed. And so this is a process that really needs to be monitored. Unfortunately, you can see from the video here that the 3D printers are very fast, and so we cannot monitor this with the human eye. So our goal here is to build an AI system that can do that monitoring for us. And conceptually, that AI system will look a little something like this. Our 3D printer will be paired with a very high-speed thermal camera, a camera that runs at least at 10,000 frames per second. And what links these two pieces of hardware is an AI module that will process videos from this thermal camera and output a signal that tells us how abnormal the printing process is. That signal can then be sent to the printer, and the printer can be adjusted to avoid causing further damage to the part that is being printed. So from an AI perspective, the challenge in getting a system like this going is really in the speed of the algorithms. We have to make some tough decisions about what algorithms we can use and how much of the video we can process. Not only that, but we also have to look at specialized hardware like GPUs and FPGAs in order to get the performance that we're looking for. Now, currently, this is research that's underway as part of the ICON Vision in the Loop project. We are able to collect high-speed video like what you see here on the left, or at least a slowed down version is what you see here. And we are able to process that video to produce a signal like what you see on the right here, where the higher the signal, the more likely we are in an abnormal printing state. The next step here is to take that signal and design control patterns that the printer can use to adjust its settings when an abnormal printing condition occurs. And our goal is to have that working by this time next year. Thank you.
All right, Brian, thanks for this wonderful introduction. Can you tell us a few words more about yourself?
Yes, so I am a researcher at the IMEC Image Processing and Interpretation Lab at Ghent University. My background is in the use of AI and computer vision in the industrial sector as well as the medical sector. And one of the projects we currently have is this Vision in the Loop project that involves multiple partners, most notably Flanders Make and Materialize. And we are looking at this 3D printing of metal parts. Yeah.
Okay. And that brings me to my first question. When you have the 3D printing of the metal parts and you're looking at what is a too high of a temperature and so on, how do you know what is too high of a temperature? Do you use explicit expert knowledge, or do you examine the pieces that you printed?
So we're sort of building on existing knowledge there. That has come from the examination of parts that have already been printed. And what we can take advantage of is the fact that for at least 90% of the time, the printing process is in a normal state. So what we can say is that most of the data we're getting with our high-speed camera should be normal.
Mm-hmm.
We're only looking for things that are infrequent or rare that deviate from that norm. So that's the foundation upon which we're going to build our algorithms. Yeah.
You call it an advantage now, but it can also be difficult, right? If you're interested in the rare event, that's a tricky situation in itself.
It can be, but what we can take advantage of is the fact that we can get a good model of what the normal state is. And then what we can report is our deviations from that normal state, regardless of what exactly that deviation looks like.
And what methods are you using there?
So in that area, we're looking more at manifold learning or anomaly detection.
Mm-hmm.
In those methods, what we really want to do is, like I said, define a subset of the data that we consider to be normal data. And then we can measure for any video frames that are coming in, we can measure how far they are away from that subset.
Mm.
And that gives us a score that we can use to say how abnormal the printing process is at any given time.
Okay, so it's different from, for example, autoencoders, which are often also used to reconstruct normal behavior and then see the difference. But that wasn't applicable in your setting, I guess.
Well, actually, it can be. In fact, that's one of the things we're looking at, where we could use an autoencoder that does sort of a compression and then decompression step. And by doing that compression, you have to throw away some information.
Mm-hmm.
And what usually gets thrown away is the more rare parts of the data set. And so when we use the autoencoder later on and put our video data into it, what we get out of it should be something that looks normal, but is as close to the input as possible. So when we compare the input to the output, that should highlight or a big difference between those two would highlight some abnormal behavior.
Well, thanks for putting it in human terms, because I realized I was turning this into an academic interview and we're in AI for Growth, so I should stay away from that.
Well.
When I see you that you're processing these videos, we're talking about images, are you using really the time series of the images? Do you, and again at risk of going a bit academic, are you putting any temporal information there where you
Yes, so we are actually looking at incorporating temporal information into the analysis. And one of the reasons we want to do that is because we want to see a stable printing process or stable temperature in the metal. So if we can look at how much that temperature varies over time, that would be a key feature to keep track of.
And I noticed in the video that you were showing that, if I understand correctly, the bright spots are the potential problematic areas. You would see those at where the line makes a little like a curve and goes back up. Is that typical because the laser stopped there for a second, or how does that?
So it's
more complicated.
It's more complicated than that, but mainly if it gets too bright or too dark as well,
no.
Those are signs that something is going wrong. Things being too bright seems to be more of a problem, because if it's not hot enough, you can always go back and heat it up a little more. If it's too hot, then you end up with situations where you're causing damage to the part
that was already printed,
previous layers, and then it's hard to really go back and correct that. So yeah, we are sort of looking for those bright spots, but at the same time, when you have too much heat on the metal, the energy starts to dig into the metal, and so you don't see it as brightness anymore because it's under the surface, and that's what makes this problem particularly challenging.
Yeah. So you cannot indeed just use the image, so you really need to examine the printed part afterwards.
Indeed.
And then given that you're in additive manufacturing or typically for small scale printing, How flexible is your solution for when you have to change something to the design? Do you have to retrain it for every design, or how does that work?
So what we're finding out through this research is that the design may influence the frequency with which abnormal behavior occurs. It might even change how that abnormal behavior looks on the camera. But the normal behavior stays relatively the same regardless of design. So, and that's the part that we're modeling. Now, it is likely the case that if you move to a different printer or a different metal, that you do have to sort of start more or less from scratch, because they will be quite different. Some transfer learning might be useful there. But we're also looking at algorithms where we learn on the fly. So for example, we'll print one layer, we'll take advantage of the fact that most of that layer should be okay, and build a model from that layer, and then use that in the next layer. Once the next layer is done, we can take that data and do a bit of retraining to improve the model and repeat and repeat. And this way we can get an AI model that is specific to the particular design and not to just any design that's placed on that printer.
Oh no, that's fascinating. So you can scale much more easily than if you can.
At least that's the hope, yes.
Indeed. And that brings me to, well, your background, you're in academia, but you are clearly industry focused. So how do you marry this challenge of building an asset that needs to advance the state of the art, but still deliver this robust value to customers?
That's always the $1 million question, isn't it? Or I guess the €1 million question. What we have to keep in mind is that there is that balance there, or that trade-off that has to be managed. So as long as all parties realize that, part of the time has to be in advancing state of the art, part of the time can be in making sure that something is industry ready, then there's room to work together. At the same time, we do try to take advantage of the fact that whenever we're advancing the state of the art, we have to compare to the existing state of the art. So what we can do is set up a collaboration where the existing state of the art is tested for industry readiness, while at the same time, in a parallel stream, we try to advance on that state of the art. That way we get hopefully two solutions, at least one of them should hopefully work.
I understand then what, as you explained earlier, in the design of your solution, the practical usability, that's another benchmark, you would say, of what makes something state of the art or not for the industrial application. So I guess that's another field that is that can help to distinguish or instill trust.
Indeed, and there is growing motivation on the academic side to see our work being used in industry, to be able to show that the work we're doing really matters in that sense. So we are open to that type of collaboration.
Okay, as evidenced by you being here. So thank you for your time today.
Yes, thank you, Mikhail.